Hello. This presentation is entitled A Full-Scale Plate-Based Tensegrity Structure as a Bike Parking Canopy. My name is Ann Sychterz, and today I'm presenting on behalf of my student. This is Heather Gathman. We are at the University of Illinois Urbana-Champaign. So first, as an introduction, tensegrity structures are composed of cables and held in tension and bars and compression, so stabilized by self-stress. These have a high strength to weight ratio and can easily be utilized for deployable applications and modular construction. So as we see here, the Carilpa Bridge in Brisbane, Australia is an example of a tensegrity inspired superstructure. And an interesting thing that came up is a plate-based tensegrity structure, as you see here on the bottom right, utilizing kind of a new element in the whole mix. So not in the traditional definition of tensegrity structure, but allowing for a plate, an actual solid surface, to be integrated into the tensegrity structure. So we'll be looking into this type of geometry for a new structure. By connecting the modules and cables in between these modules, we can now create a modular larger structure composed of these plate-based tensegrity units. So what's interesting is that they're modular. So first of all, that's easy for construction, maybe more so than our other construction methods, more typical construction methods. There is an architectural appeal because it is more of an exposed structure. Next thing is that we can utilize the shape of an arch or different things, even by curve structure, so that we can kind of appeal to the architectural nature of a new building. And so you can see here kind of the conventional shapes of structures, with the last one on the right being a possible plate tensegrity canopy. So aluminum as a construction material is quite interesting. It's energy efficient, sustainable in terms of its recyclability. Yes, you need energy to harvest it, to mine it in the first place. However, it's lightweight, so it's a third of the weight of steel. It's corrosion resistant, and there's minimal maintenance just due to it's not necessary to paint aluminum for protection against rust. It's indefinitely recyclable and easily extrudable, which means that the shapes that we can get with aluminum can be quite customizable. So what we're proposing is an aluminum plate-based tensegrity structure as a bike parking canopy on the south side of Newmark Civil Engineering Building at the University of Illinois. So on the left-hand side there, you can see a map of where we'd be locating the structure. And this is part of the Sustainability Living Lab initiative here on campus. And on the right-hand side is a rendering of the structure. It has a bit of a double curvature in one direction. The overall width is approximately 2.4 meters, a depth of about 1.2 to be placed a part of the bike parking to provide shelter due to the elements. And these plates are about 30 centimeters by 30 centimeters, so easily manipulable by individuals, and 1.59 millimeter stainless steel braided cables. And then the aluminum square tubes is approximately 15 centimeters square hollow sections. So here we use dynamic relaxation as a method to analyze both the individual modules and also the whole structure using the N5B8 method as shown by Filipov here. But then the plate is kind of taking inspiration from origami, and the cables and struts are kind of the standard that we have been modeling tensegrity structures as previously. So you can see here, this is the roof structure with the cross section with that curvature that I mentioned previously. We tested it for our typical load cases for snow, wind, dead, also for critical cases such as vandalism, if someone wanted to hang on it, because it is on campus, so things can happen. So we checked all of those and made the sizing appropriately. Looking at the deflection, this is exaggerated, but looking at the load cases due to vertical downward loads and also uplift due to wind. So we're in less than level 360, so we're okay. Look at the load cases. We're getting maximum stresses in the cables, well within the limits of the cables and the struts. The struts are aluminum. And so moving forward, we also had to design the joints as well. So these are all tabs slotted and adhesively joined to that center cylinder using the JB weld. And so this is a very repeatable and easy process. So we can be done on campus, very strong. And so this is in process actually right now. But we did some structural testing to make sure that our process, both for the cables and the tabs, are going to meet our standards. So we did some load testing. As you can see, the tabs there on the left-hand side with the downward direction load. And then on the right-hand side there, we loaded it up to, it was over 930 newtons. So our demand was about 685. So we're going to be in a decent range there. So just to conclude is that we were using dynamic relaxation, an equivalent framework for showing that the plate-based tensegrity structure is feasible, or to also make our design sizing. This is for a bike parking canopy, so it's within the, it's going to be outside, so it's within our ASC 7 loading limits. And interestingly, like we're using aluminum because it's something that can be aesthetically pleasing on campus. So we're trying to tie into some sustainability aspects there. With that, I'd like to thank you for your attention.